Welcome back to the Mechanics of Solids lecture series. We're working examples solving for shear and bending moment diagrams using a set of simple rules. The next example that we'll look at is a cantilever beam with a distributed load over part of the end of the beam. We'll start by solving for the reactions. I know that at the support A, I'll develop a reaction in the y direction, which I'll call A sub y, and I'll develop a concentrated moment, which I'll call M sub A. I'm drawing them in the assumed positive direction. If they're negative, it should come out in the math. Let's start with sum of the forces in y equal to 0. We have A sub y minus the contribution to the load, W, times the distance over which it acts, L over 2, equals 0. That tells us that A sub y equals WL over 2. To solve for the concentrated moment, I'll take some moments about A equal to 0, positive in the counterclockwise direction. The concentrated moment M sub A itself produces a negative moment about A, and the concentrated load W also produces a negative moment about A according to that sign convention. Its value would be equal to WL over 2, which is the magnitude of the force, acting in the center, times the distance, which would be L over 2, plus 1/2 of L over 2, for a sum of 3/4 L. So multiply that by 3/4 L, set that equal to 0, and that tells us that M sub A is equal to 3/8 times WL squared. Notice I couldn't use the shortcut rule, the WL squared over 2, because the concentrated moment didn't extend all the way to the end of the, or because the distributed load didn't extend all the way to the end of the beam. Okay, so sketching in what I found out, A sub y equal to WL over 2, the concentrated moment equal to 3/8 WL squared, but actually acting in the opposite direction of what I assumed. Okay, let's proceed to solve the shear force diagram. To start, we have a reaction acting upward, so the shear force diagram is going to jump up by an amount WL over 2. There's no load over the beam from A to B, so the shear force is going to be constant from A to B, and I draw a straight line going across. And then when we reach the distributed load, because we have a constant distributed load, we know the shear force diagram is going to be linear. Since the distributed load is acting downward, shear force is going to decrease. And I can draw this as a straight line to the end. I know it comes back to 0 because there's no concentrated reaction at the end. But let's check that. The shear at point B, WL over 2, minus the distributed load W times the length over which it acts. And that indeed does come back to 0. Now for the bending moment diagram. To start, the bending moment drops down by an amount equal to the concentrated load, 3/8 WL squared, the concentrated moment, reaction moment. Because the moment is in the counterclockwise direction, bending moment diagram jumps down. Now, the shear force diagram is constant, so the bending moment diagram is going to be linear over this region from A to B. Shear force is positive, so bending moment will increase linearly. So I'm going to draw it something like that. Okay? To get the value at point B, I will take the value at point A, which is negative 3/8 WL squared. Going to add to that the area of the shear force diagram from A to B, which is WL over 2 times L over 2, WL squared over 4, which is going to compute to negative 1/8 WL squared. So that's my value at point B, WL squared over 8. Finally, in the final region from B to C, shear force is linear, so the bending moment is going to be quadratic. Shear force is positive, so the bending moment diagram is going to increase. So we have a quadratic curve increasing, and we know it has to come back to 0. So I'm going to sketch it something like this. So I knew the curve was quadratic, but how did I know the slope? I knew that at the end the shear force is 0, so the slope has to be 0. And where the shear force is larger, the slope has to be larger. That's how I knew to draw the curve like this. Okay, value is negative. Now let's check that it came back to 0. WL squared over 8, negative WL squared over 8, minus, or plus the area of the shear force diagram from B to C, which would be 1/2 WL over 2 times the length L over 2, and that is also WL squared over 8, so it does come back to 0.